pi bond we've got, we'll add the hydrogen across it, and we'll reduce all the way down. Esters and carboxylic acids have the same issue as they had with the lithium aluminum hydride. Their first reduction takes them to that acetal, that carbon with two oxygens attached to it. That is an unstable structure that falls apart and goes down to the ketone, or that goes down to the carbonyl. Okay, so it cleaves off the OR group or the OH group, and it goes down to the carbonyl. Once we're at the carbonyl, we again still have a pi bond. Hydrogen can react again, put another hydrogen on, and we end up with our alcohols. Okay. The reason why this becomes important is actually going to be the next slide, which is looking at a quiz. Okay. So what happens if in our structure we have a carbonyl and we have an alkene? If we use H2, both the carbonyl and the alkene get reduced. But what if I just want the carbonyl reduced? Hydrogen and platinum won't work because that takes care of my alkene at the same time. So what I'm going to have to do is switch the chemistry around or pick a different reagent to allow for that to occur. That's when I might use sodium borohydride, because sodium borohydride won't react with the alkene, but it will react with the carbonyl. Same deal, same option with the lithium aluminum hydride. We could add the lithium aluminum hydride to react it as opposed to H2 with platinum or palladium. Okay, questions on this slide? Okay, we'll take you to the quiz. Would have been nice if it had actually frozen. What was the result of this reaction? What would we end up with? I said we had this, right? Let's change that R. How does that change the product? I need that big long chain, right? How does that change the product? I need that big long chain. How does that change the product? What does that mean? It breaks the ring open. These intramolecular ring opening and ring closing reactions are notoriously difficult to see. Okay? Focus on the chemistry. Just because it's a ring doesn't mean you can't break the ring. The chemistry is focused on that bond. That bond breaks. I don't care what's out here. Completely irrelevant. Okay? Very, very tricky. It's a famous question on a lot of ACS tests, that kind of idea. Both the ring openings and the ring closings. Okay, so watch out for that. Ow. We should have about 10 minutes left to look at synthesis questions. So reactions of alcohols, the last section in chapter 12 looks at our oxidation reactions. So we looked at some kind of generic ideas within the reduction and identifying oxidation states. When we're looking at our oxidation reactions, we're looking at the acidic hydrogen off of our oxygen. Out here, we're looking at that guy. We're also looking at this oxygen being nucleophilic. And then when we had this slide up initially, we'd said acidic hydrogen, kind of weird hydrogen. And I was intimating at that point, intimating, is that a word? Okay. Hinting at using that hydrogen. The hydrogen we're going to look at for the oxidation is not that hydrogen. It's a hydrogen here. That hydrogen becomes acidic in our oxidation reactions. Okay? Very odd, because in our reduction we supplied a negative hydrogen. If we're going to do the reverse in oxidation, we would assume that a negative hydrogen comes off the structure. At no point does a negative hydrogen exist in our oxidation reactions. Okay? Kind of odd. Sorry, jumped ahead a little bit. We did talk about this in lab, though. When we look at our alcohols, we've got primary, secondary, and tertiary alcohols. To go through and do the oxidation, we need a hydrogen attached to our alcoholic carbon. So in the case of our primary alcohol, there are 2 hydrogens present. In the case of our secondary, there's 1. In the case of our tertiary, there's none. To go through and do the oxidation, what we're doing, you'll notice, is we remove a hydrogen in each of these oxidation steps. Well, what if we don't have a hydrogen? In the case of the tertiary alcohol, there's no hydrogen to remove, which means nothing happens. Okay, we're left with our tertiary alcohol. When we look at our primary alcohol, we can remove one hydrogen, but then we still have a second, which means we now have a second opportunity to oxidize. Okay? When we do that second oxidation, we are just increasing the number of oxygen bonds, and everybody looks at it and says, oh, that looks kind of weird. Okay, all we're doing is adding just another oxygen to our structure. It just happens to add it, we also have to include a hydrogen because oxygen needs two bonds. So in our oxidations, we'll almost always run under acidic conditions so that we can get that last proton onto our oxygen from our carboxylic acid. Okay? So those are our oxidative steps that we've got access to and how we can go through and run these. So if you see a tertiary alcohol, you don't touch it, you leave it alone under oxidative conditions. Our primary and secondary can do oxidation reactions. Our secondary are really nice. Why is it nice to see a secondary alcohol running under oxidative conditions? There's only one product. It can only go to the carbonyl. Or officially to the what functional group? Ketone. If we look at our primary alcohols, those get tricky because those have two oxidative steps that could happen. So depending on the activity of my oxidizing agent, I may stop at the aldehyde. I might continue all the way to the acid. Okay, and that's what makes our reagents a little bit interesting. As far as the lecture goes, there's really only two oxidizing agents that you need to know about, okay, with alcohols at least. Chromic acid and PCC, or how I like to refer to it is politically correct chromic acid. Okay, for those of you that missed the lab, because you aren't in it, okay, if you think about politically correct humor, what's going on with politically correct humor? It's usually pretty boring and not very funny. Okay? It's a milder version of the incorrect humor. Same thing's happening with PCC. Okay, so PCC is your politically correct chromic acid. It just cannot oxidize all the way. So that means when we go through and look at our reagents, when we take a primary alcohol with chromic acid, I cannot make the aldehyde, okay, or cannot isolate it. That chromic acid is just such a strong oxidizing agent that that will take the primary alcohol all the way down to the carboxylic acid. Right, if we look at the secondary alcohol, chromic acid will stop at our ketone. It can't go any further. Why not? Why is it done? There's no more hydrogens that I can remove from the structure or from that carbon to do the oxidation. When we look at PCC, okay, PCC with a primary alcohol stops at the aldehyde, and it stops there because the PC portion of our chromic acid neutralizes the overall reactivity, and we don't see it go all the way to the carboxylic acid. So as far as what you need to know, as far as your oxidation agents go, is if you've got chromic acid, oxidize the crap out of it. Oxidize it till you're done. Okay, you can't oxidize anymore. If you've got PCC, you do a single oxidative step to the carbonyl. What if you start with a carbonyl? No reaction. PCC reacts with the alcohols. It will only oxidize the alcohols. It's not going to touch the carbonyls. All right? That's the be-all, end-all story of our oxidation reagents. Okay? Questions about that? Because the next part of it is looking at mechanisms, which I'm probably going to try and keep that at 5 minutes.
So chromic acid will react with carbonyl?
It will react with alcohols and carbonyls. Good point. What if you start with the aldehyde? What happens with chromic acid? We'll take it to the carboxylic acid. So if you have a structure that you start with an aldehyde, you go, oh, I don't have an alcohol, so none of my reagents will work. No. The aldehyde will still react with the chromic acid. Okay. But not PCC. Okay. Questions? Okay, I'm going to go ahead and click the next one because I didn't draw anything extra on this. So now we'll look briefly at the mechanism of oxidation and ultimately get at the idea of why is there a difference between PCC and chromic acid. When we look at the reagents, chromic acid is typically run with H2SO4 and water. So this is our chromic acid solvent, if you will, water. PCC's solvent is technically pyridine, but because it's acidic, it becomes pyridinium. Okay, so those are the two species that are really present. And we've got, might as well tag it up here, H2SO4, and then our pyridine, just with the nitrogen in there. Okay. The difference between these, or the activity of these reactions, comes back to those, or that difference in reagents between those two different reactions. We're still looking at chromic acid being the active oxidizing agent in both reactions. Okay, what we're concerned about is that secondary contributor. That secondary contributor is what's adjusting how this reaction works. So in a very approximate mechanism, how might we add some arrows into this? And yes, this is going to be god-awful approximate. We look at those starting materials, those two things. Let's assume we can't see what's coming after it. Those two things. What looks to be the most reactive? Right, and by most reactive, what are we looking for? What makes it unstable? Charge. So we're going to try and look for a charge within there. What charges do you see within those first two structures? And by first two, I guess we should be clear. We're now looking at our reaction, these two down here. Well, we got an alcohol functional group, so you should be telling me the carbon's positive, the oxygen's negative, and the hydrogen's positive. Okay? But then we move to the chromic acid. What do we say about the hydrogens? The hydrogens on chromic acid, are they positive, negative, neutral? Why are they positive? For the exact same reason the hydrogen was positive on the alcohol. Okay, they're attached to an oxygen that's pulling electron density away. Okay? We could argue that it's chromic acid, which means the hydrogens on chromic acid are more or less positive than on the alcohol. What is the definition of an acid? What charge are our protons? Positive. What atom holds the positive charge? Hydrogen. So chromic acid has positive hydrogens, so positive that we call it an acid. What's the positive charge on our alcohol? Is it bigger or smaller? Much, much smaller. Hence we call our alcohol an alcohol, not an acid. Okay, so our chromic acid has much more positive hydrogens. So the hydrogen choice that we looked at the alcohol was a bad option. Okay, we could look at the oxygen being negative. Okay, let's compare our oxygens. Which oxygen is more negative, the one on our alcohol or the ones in our chromic acid? The one in the chromic acid has resonance, which means what happens to the negativity of our oxygens in chromic acid versus the negativity of our oxygen in our alcohol? Becomes less in the chromic acid, which means what did we just find in our alcohol? We just found a partial negative on the oxygen. That's the most negative atom in our structure. The carbon in our alcohol, we said that was positive. What's positive in our chromic acid? The hydrogens and chromium. Which is more positive, the chromium or the carbon? Chromium, what does that mean? When we run a reaction, what do? We find the negative and we attach it to positive. What did we just find? The negative and positive. So we're going to look at a reaction, more than likely, what we're saying is our oxygen attacks our chromium. If we take a look at what I've got drawn, what happened? Well, look at that. The oxygen of my alcohol is attached to the chromium. Hey, fantastic. What else changed? It lost an OH. OH is a horrible leaving group, so what happens? It picks up a hydrogen and then leaves as H2O. What else happened to our alcohol? It took its electrons away from hydrogen. So we've now combined probably 3 different mechanistic steps. Hence, if we take a look at the reaction arrows, how many reaction arrows did I give you? Ta-da, 1, 2, 3. 3 mechanistic steps, because we just crammed 3 mechanisms into one step. We end up with this goofy looking intermediate. Okay. What happens now to go from this intermediate to our product? And maybe as a hint, would you like to enlighten us? So you're saying this? Let's have the base attack the hydrogen, which means the electrons in that bond go where? Go to the carbon-oxygen pi bond. But now oxygen has too many electrons, so what happens? It shuttles those electrons over to the chromium. Okay. Yes, some more goofy kind of things happen around that OH. And we'll end up with our chromium trioxide as an end product. What we've done is taken our alcohol down to the aldehyde. Okay? The aldehyde is really the crux of our argument on deciding this next sequence. If it's PCC, we stop right here. Okay? The argument that we could come up with is that PCC is a sterically hindered, or wait a second, where am I? Oh, our pyridinium is a weaker acid than sulfuric acid, which means that step where we had our OH pick up a hydrogen isn't as active. If that step's not as active, can we go through for the next oxidation step? Probably not. Okay, so the sulfuric acid can help facilitate the initial attack. Okay? The next issue we run into is that for our next reaction to occur, and actually now I'm a little bit nervous, do I have the next drawing up? Ah, I do. Right? For the next reaction, we take our aldehyde, and it reacts with water to form this special species. What was special about this species? What was this one known as? Acetal. So trying to not sound bad, the as part of what you were saying was correct. Okay. We're looking at an acetal. What's special about the acetal? What do we see now? We see the presence of an alcohol, which can do what? Act as a nucleophile to attack the chromium. When we look at our aldehyde, we don't see that alcohol. It can't attack the chromium. We went back to our previous mechanism. What happened? The alcohol is what attacked the chromium. It's what initiated this whole cascade to go through and do the oxidation. If we don't have the alcohol, we can't do that attack. So in the presence of water, water reacts with our aldehyde to form the acetal, which gives me the alcohol. Now that I have the alcohol can react with the chromic acid, and we can go through and oxidize off yet another hydrogen. Okay? That ends up pushing us all the way down to the carboxylic acid, which mechanistically I'm not going to draw up here because it, again, isn't that big of a deal. What's more important is to know where the difference is between these. Chromic acid, right, supplies that H2SO4. That facilitates this first step. Okay? So because H2SO4 is a stronger acid than our pyridinium in our PCC, that step is now superactive. Okay? We have a similar version of that step in this next sequence, okay? When our alcohol or our diol reacts with chromic acid. Okay? We still need that strong acid. Our pyridinium doesn't supply that strong acid characteristic. That attack isn't as likely to occur. The next really huge big difference is that when we look at chromic acid, we've supplied water. Water can act as a nucleophile with the carbonyl, giving us that diol structure. The diol is what can then move forward and react with our chromic acid. Okay? And since our pyridinium can't act as a nucleophile, it can't generate that diol species. Without the alcohol, we can't do that oxidation. Okay? If anybody is interested in seeing the rest of that mechanism, you are more than welcome to talk to me after class. I'm more than happy to go through it, but we're not going to deal with that now. The overall summary or the story of this is that what we're looking at is chromic acid and PCC. Okay? I know this looks a bit busy, but what we're looking at is a primary alcohol reacting with chromic acid versus a secondary versus a tertiary, or with PCC, a primary alcohol versus a secondary. Okay? I've got it organized in this fashion so I can try and keep all of them on the same page. Okay? That's what you're responsible for knowing out of our oxidation chapters, or out of our oxidation. Questions about that? Okay, this is summarized. You do have this available to you. The only thing that's different is that that primary, secondary, tertiary labeling I just put on it wasn't on it originally. That's the only scrawl thing that I've added to it. Okay? Synthesis of our alcohols, addition. I'm really not going to talk about this section because it's really just a review of chapter 10. Okay? So these are all of the reactions from chapter, I think it's 10, maybe it's 9. One of your chapters that looks at alkene additions. These are all the reagents that end with alcohol functional groups. Okay? So you are expected to know these and use them. Yeah, I know, they came from first semester. Deal with it. You got to know them for this semester too. Okay? If you've got questions about how any of those react, please talk to me. I'm more than happy to go through and show you the results of how they work out. Okay? I did try to imply stereochemistry where it was really important. You'll notice that I didn't specify for the mercuration for the hydroboration. The hydroboration reaction, right, does have really important stereochemistry concerns. Oh, that was a horrible. If we make the OH wedged, our hydrogen will have added wedged as well. Okay, so that's one extra little step on that as far as the stereochemistry. The mercuration reaction is sort of selective at first, but then you lose selectivity in the second step. Okay, so there is no real stereochemistry concern there. You end up with enantiomers. Quick notes. That's just kind of the overall summary of what things act as. So in our BH3, boron acts as the positive, our hydrogen acts as the negative. That's the interesting reaction because we get the non-Markovnikov result. Okay, the OH, or our hydrogen, goes to the most substituted as opposed to the least substituted. The mercuration reaction is the exact same result as if you added just H3O+, except if we react with H3O+, we form a carbocation. What can carbocations do? They can rearrange. The mercury reagent does not form the carbocation, so we don't have to worry about rearrangements. Okay. The Br2 and H2O reaction can be switched around a lot. All you end up doing is changing the H2O for any kind of nucleophile. Okay. Any kind of weak nucleophile, and that will work for there. Okay. Because I really actually wanted to get into the synthesis, and I don't like that question as much. Well, sure, why not? When it comes to synthesis, Okay? With your synthesis questions, I feel that a lot of people tend to have problems with them for a couple reasons. The primary reason, you need to know all of your reagents. If you have any weak points with your reagents, if one of those reagents shows up in the synthesis, you're now screwed. Okay? You can't solve the question. So when you look at a synthesis question, you should have every single reagent out in front of you that you're aware of. You should have tables of reagents. You would think that somebody would have compiled something and posted that information available somewhere. It's all over the internet. It's also on Canvas. I've posted information like that. So go through, take a look at the information that I've posted. You do have access to a lot of summaries of the reactions that you've seen already. Okay? The next part is kind of a general breakdown on how I would go through and approach a synthesis question. So we're usually given the reactant. So identify where it's reactive. Okay, so every time we've addressed a new functional group, we talk about its reactivity. So if I take a look at this functional group, what functional group do I have in my reactant? First off, what functional group is that? We have an alkyne. How do alkynes react? They act as an electron source through the pi bond, so we can run an addition reaction. What else do they do? They have an acidic hydrogen. What's special about an acidic hydrogen? I can make the carbon a strong nucleophile by removing that hydrogen. Okay? The next part that I would go through and do is look at the product and do the same thing. Where are sites of reactivity? I would identify those two carbons as massively important carbons. Okay, why? Why are those carbons my big reactive ones? That's actually the next question, so we won't even worry about that yet. So this has nothing to do with what I'm starting with. I'm completely ignoring what I'm starting with, but I focus on those two carbons. Why those two carbons? They're charged. They're partially charged because of the bromines. That means there is some reactivity at those two carbons, which means if I'm going to think backwards, I'm thinking backwards around those two carbons first because they have obvious chemistry. Okay? Identify if there are constraints on these sources of carbons or reagents. In general, because my library of questions within synthesis is fairly new, I don't have a lot of constraints. I'm pretty much giving you, if here's a starting material, here's a product, do whatever you got to do to make those connections. There are no limitations on how many carbons you can bring in or where your carbons come from. Okay? If you happen to take this class with other lecturers do incorporate restrictions. Okay? I've seen some say that you cannot bring any more carbons into this structure. Okay? If you do incorporate more carbons, you can't add more than one carbon at a time. Okay? So be aware of those rules when attempting to solve. With the ACS test, we don't have to worry about those rules because they're usually very straightforward with that. That's what happens with multiple choice. Identify any major functional group changes. So what functional groups changed? I went from an alkyne to, I wouldn't actually say alkane. Went to halides. Yes, there is an alkane functional group there, but we'll address why we don't want to look at that quite yet. Okay, we went to halides, which means in the course of this reaction, what do I have to do? What type of reaction? Addition. Okay? Addition has to happen. I lost pi bonds. Okay? I'm now whittling down what reagents can potentially get used. Okay? The next part, identify the carbon skeleton. And this is where both of you were actually going. You saw the red carbons and said, hey, those are the starting material red carbons. That's what I'm asking for identify the carbon skeleton. What we're trying to find is where did those starting material carbons go? Okay? And I completely agree with you. The red carbons that are circled there, yeah, are probably the starting material carbons. Which means what? In the course of this reaction, I had better supply that giant thing. Which means I'm going to have to do what type of a reaction? Can I do an addition with a giant carbon structure? No, the only reaction that we have to be able to do that is a substitution. Okay? And then do you have to move reactivity? So if it looks like the reactivity has changed from one carbon to another, that's an important thing to do or notice. If reactivity has changed locations, pretty much the only way to do that is to get to an alkene, because alkenes have reactivity at 2 positions in your carbon structure. Whereas other functional groups really only have reactivity at 1 carbon. Okay? Now with all of this information, I'd start to process through it and see what I can do. Personally, I see the addition as the easiest thing to work with. Okay? So I would say, you know what, let's do that addition reaction now. I'm going to add Br2. Well, how many bromines did I add? I added 4 bromines, which is the equivalent to doing 2 additions of bromine. If I did that, what functional group would have to connect those red carbons? I need 1 pi bond to put on 2 bromines. If I've got 4 bromines, 2 pi bonds. What makes this really cool? Hey now, that's starting to look like my starting material. Okay? So now again, I got to start to look backwards. Okay, or at least I start to look backwards and think, okay, what's missing? Hydrogens are going to be implied off of this structure. Whoops, sorry, that's what I was missing here. We're now missing that structure, right? That was still attached to it. We didn't remove that. Sorry, I didn't see that. So does anybody see a weak bond that we could look at now between our starting material and now our new product? What do you mean the hydrogens? So let's go with you first. What hydrogen are you talking about?
They're both symmetrical. So.
On the starting material or our product? Starting material. We've lost a hydrogen. Okay. How can we remove that hydrogen? We could add a base. Here's where you can get partial credit by just writing a base. Where can you get full credit? You tell me what the actual base is, and in this case, the best base to be would be sodium amide is what we've talked about, and I think you just said sodium hydride. I'd accept sodium hydride as well. Interesting. This species is now what? Charged. What would it act as? A nucleophile. Where is this carbon, my green starred carbon now, in my product? It's the one attached to the ring. If I know that carbon is partially negative, what charge does this carbon need to be? Partially positive. So somehow or another, what I'm going to do is run this reaction where I now bring in that carbon structure where that carbon is positive. We can't show a formal charge. It has to be neutralized. So what do we put on it? What leaving group do we put on it? Why bromine and not something like OH? It's a good leaving group. OH isn't as good of a leaving group. There's another big issue with OH. It brings in an acidic hydrogen that could react with, say, a basic carbon that we just made in the previous step. Okay, kind of makes sense? Okay, we are officially done. Okay, I do want to throw up another synthesis question, so those of you that have time can go through and try and piece it together, come up with your own ideas on how to go through and approach it. Are there questions on this before I stop the recording and let you guys do whatever you need to do? Okay. Last thing actually before you completely decide that you're done with it, go through and do each step, beginning to end. Okay? Don't look at where you're ending, just look at what you would expect to happen at each step. Verify that it actually makes sense. Okay?